Hello and welcome to the Transport Phenomena Final Project for Matthew Lauderhand, Milad Jafari, and Richard Farrell. For our project, we were investigating primarily TRAIL, or tumor necrosis factor-related apoptosis-inducing ligand, and the relative tubing associated with it, and particularly the transport phenomena concepts of how flow rate and pressure vary with respect to changing tube diameter and length. Move on. Now, with the introduction, we want to go over the basic concepts of this paper that we found and how it relates to the transport phenomena as a whole and our model. So, a recent study has devised a method to capture circulating tumor carcinoma cells, or circulating tumor cells are primarily known as CTCs, and CTCs usually come from what is known as just tumors, and they slough off and go into the bloodstream. And these CTCs are very dangerous and of primary interest of clinical studies because they are able to move through the bloodstream and deposit at secondary sites. They are what's known as inducing metastasis, which is a very dangerous concept in cancer as a whole. It is the formation of secondary sites, but even before a cancer is considered metastatic, these CTCs are already in the bloodstream and going throughout the body, looking for secondary sites. So ideally, getting rid of these CTCs is very important to helping improve the outcomes, patient outcomes for one, and also as a therapeutic standpoint and study standpoint, where we can take these CTCs and study them for later analysis. Now, this study was primarily confirmed with removing CTCs as they induce apoptosis or cell death. Now, the study has shown preliminary efficacy in killing cancer cells within the blood, and it had an increased efficiency over an aspirin treatment control, in which they just treated the cells with aspirin and killed them. Now, apoptosis was achieved by separating the cancer cells from the bulk flow, and this was primarily done in Figure 1a. As you can see, as margination, the separation of the larger cells from the bulk of the flow, or of the red blood cells. And these cancer cells are taken towards the outer surfaces or the outer borders of the tube, in which they stick upon the inside surface through E-selectin, which is coating the entirety of the surface of the tube, along with TRAIL, which again is the apoptosis-inducing ligand. Now, the great thing about this TRAIL is that it affects cancer cells, but does not affect non-cancerous cells, which makes it very effective at particularly removing cancer cells from the bloodstream, as it doesn't affect anything else. Now, as these tumor cells are taken with towards the outer border and rolled along the surface of the inside wall, they interact with the TRAIL and primarily through the receptors on the outside of the cell die. They are detached from the wall and go back into the bloodstream after rolling for a bit, and then they undergo apoptosis. And the study found that there was a markedly reduced number of CTCs in the bloodstream, enough to be statistically significant, and also had a improvement in CTC's volume when compared against the aspirin treatment control again. So the primary concepts in transport phenomena that were of interest to us are in Figure 1b and 1c. Now, these are the rolling velocity and the rolling flux as functions of wall shear stress. So the rolling velocity and the rolling flux in this study were found to be the most effective measures of how the cancer cells were successfully affected by TRAIL. The study described that rolling velocity and rolling flux as the cells rolled along the TRAIL and the E-selectin at a certain pace and also of a certain amount of cancer cells rolling through at a time. They found that specific values, like a higher velocity and a higher flux, meant that they were rolling faster, and they wanted to try and mediate and see which values of these rolling flux and rolling velocity were most effective at the cancer cell retention and apoptosis inducing. Now, the study primarily found that at a wall shear stress of 2 dynes per centimeter squared, the maximum efficiency for rolling flux and rolling velocity was found, as these cancer cells were efficiently rolled, not too fast, and also not too slow, with the E-selectin at a constant concentration of 2 micrograms per milliliter. Now, the reason why we looked at wall shear stress in particular was because as these cancer cells are effectively at the border because they are so small, we can effectively use wall shear stress. And additionally, the wall shear stress is imparting the rolling force on the tumor cell as it is rolling the blood along the top of the surface, and the bulk flow is pushing these and rolling these cells along. We can go to the next slide. Now, the clinical significance is, again, as the trail receptors do not target non-cancerous cells, the methodology in trapping and releasing cancer cells to undergo apoptosis may be an effective strategy at treating the presence of CTCs in the blood. However, the extremely small tube diameter used in this preliminary study at just 300 micrometers meant that scalability of this setup would require further investigation, and that's where we wanted to come in. So the small diameter tubing obviously results in a lower flow rate and the amount of volume being pushed through the tube. Smaller tube means you can't have as much in at a time. And if this is only one 300 micrometer tube, you're either going to need a very long tube or a very fast flow rate to push this reliably through, which could cause a slew of complications for the patient. So what we wanted to look at was if we could effectively, theoretically, increase the diameter of this tubing and the length, we could mimic certain conditions like in hemodialysis, which already takes a very long amount of time, hours at a time usually, to filter a patient's full amount of blood. So at just 300 micrometers, it would take even more. So the scalability is what we wanted to look at. So by potentially increasing the length and diameter of the tubing, we can have a higher volume of blood pushed through the entire setup, thus improving the quality of life because the patient's not sitting there for however many hours at a time. And also, it potentially increases the number of CTCs that are successfully targeted by the trail. As they move along this trail covered tubing, there is a longer length, which means a longer amount of time that they are able to roll along the tube to begin with, and also a better chance of them rolling at some point, and thus a higher chance of the CTCs having apoptosis induced. However, a larger tube changes the flow rate, which would additionally change the shear stress upon the wall. Now, recall that the wall shear stress was 2 dynes per centimeter squared, and that was the most effective rolling flux and rolling velocity at the constant concentration of 2 micrograms per milliliter of the E-selectin. So given that the most effective shear stress was that 2 dynes per centimeter squared value, how we account for changing the flow rate and the pressure to retain a constant wall shear stress at that value, even with a change in diameter and length of tubing, because we still want to retain that maximum wall effectiveness of the with the wall shear stress value. So that was what we wanted to investigate primarily in our model. And we can go into the next slide.
So there's a list of broad assumptions that we made for our model in this project. We modeled our device under the assumption that is a cylindrical geometry, previous slide. And we wanted to keep it in mind similar to that of a hemodialysis machine. And what's important to note is that the shear stress at the wall is approximately equal to the shear stress at the cell when we want to, again, maintain that 2 dyne per centimeter squared for the maximum efficiency, as that in the study showed that the cancer cells would be binding to more E-selectin efficiently without detaching from the ligand. So we wanted to continuously roll through Rubicons continuously roll along the tube wall so it binds some more ligand. Ferrous Lindquist was a concept that we were considering in this model. However, it was not directly applied, as the original study itself didn't explain the mechanics of the tubing, so there was not a lot to go off of to suggest Ferrous Lindquist, other than the fact that the original tube diameter was less than 500 microns. However, in this study, we observed how changes to the diameter and radius of the tube would affect the parameters, including a change in pressure, flow rate, and much more. One of the other assumptions that we made is the viscosity of the blood would remain at a constant 3 centipoise, as in table 4.6, next 2 slides, showed that the viscosity of the blood would stay at 130 microns at 3 centipoise at 130 microns. So we assume that it would continue to stay that way in this model. Another huge assumption that we made in this study was that the flow would be laminar consistently throughout the tube. That is because if we conceptually think about it, the blood has to come in and out of the tubing at a normal pace, and it shouldn't be vehemently moving out of the system, or else complications could arise. So the flow should be laminar and should be moving at a rather steady pace. Now, we confirmed this using Reynolds number, and in order to calculate Reynolds number, we had to make some assumptions. Next slide. Based off the properties of blood. So we know that blood has whole viscosity of 3 centipoise. And next slide. And we have to know what the velocity of the blood is as well. We already know what the length is of the tube. Length is from the study it was 0.5 meters, and that was also adjusted as well with continuous parameters in our study showing the results. We couldn't solve for the velocity because there was no information provided, so we had to use a relationship between flow rate and pipe diameter. I see how those change, that would affect the velocity, which would then affect Reynolds number. And we consistently found that Reynolds number was below 2300, which is the threshold for which flow is laminar through a cylindrical tube. Previous slide. So the remaining assumptions that we made in this study was that there is high shear rate, focusing on the edge of the vessel, since that is where shear rate is the highest. And one big challenge that we encounter in the model is how we can account for the flow rate change with the associated wall shear stress of the two dynes. And the intermediate that we found to connect these two was reduced average velocity, which is a direct function of wall shear stress. And so once we could solve for average velocity, next slide, it was shown that average velocity was related to, or is related to, flow rate, shown in the bottom, 4q over pi dq, with the diameter of the tube as well. And then that, in the figure above, could be seen that it could be approximated based off of the wall shear stress of two dynes. It's approximated at 4 per second, so that was kept constant, as well as a wall shear stress. Previous slide. So that's how we kept maintaining that for our model, was keeping that value consistent with the wall shear stress. And then the last assumption we made was, or the last two assumptions we made was, one, the model was in vitro, and also the other one was physiological conditions, as said before, that the temperature would be at 37 degrees Celsius to account for the blood being the fluid that has to be in normal conditions, knowing that the fact that blood is a non-Newtonian cast-on fluid. Next slide.
So, for our results, we saw some trends particularly associated with the dimension as to what had to be manipulated with the pressure in order to maintain the shear rate, and based on the changes in diameter and rate and length. So we found that as we increased the length of the tube, there was a linear relationship with the amount of pressure you had to apply in order to keep the flow rate and the shear rate at the edge of the tube the same, which is what we would expect based off of the equation shown here for the reduced average velocity, or not for the shear wall shear stress, where it is in direct relation to the radius and the length. As you increase the length, the flow rate did not increase, however, as the shear did not, it's based off the pressure differential, which resulted in the same shear when you applied this linear relationship, giving a consistent flow rate for each of the tube diameters depending on the diameter of the tube. For the radius increases, because radius is has a two-dimensional impact on the flow, it had a logarithmic effect on the pressure and flow rate. So if you took the log of the radius and the log of the pressure, or the log of the radius here and the log of the flow rate, you would get linear relationships. However, as you increase the radius, the pressure needed per area will drop off, as the shear rate is very small near the outside, and so if you had too much pressure, it would overrun that. And as the shear force, and as you increase the radius, you need the flow rate overall to be higher in order to keep that shear force the same. Over here, we have flow rate changes. So as we increased the diameter of the tubes and increased the length of the tubes, both measured in meters, we saw that we had to drastically increase the flow rate in order to compensate and keep the shear at the same level. And a similar pattern, but a drop-off, was noted for the pressure. As you increased the length, you had to increase the pressure. However, as you increased the diameter, you had to decrease the pressure in order to maintain the shear rate. For our methodology, we were trying to, just as an overview, we're trying to increase the radius of the tube to increase the amount of blood that could get filtered. We decided to increase the length as well to increase the amount of blood that was getting filtered and the efficiency of the filtering. So the idea was it would give the fluid inside the tube more surface area to interact with when you increase the length, and increasing the radius would allow you to filter more blood at the same time. There are consequences of this kind of balancing, however. Surface area to volume ratios were not directly considered for this modeling process. We did try to compensate to an extent by increasing the length of the tubing that the blood was going through. However, we did not model the surface area to volume ratios in order to see what impact that would have on the amount of blood being filtered, or amount of cancer that would get filtered out. Additionally, there's general parameters that you have to use if you're applying it to a person. So the tube has to hold a reasonable amount of fluid. You cannot put more blood into the tube than you have in a person, because then there'd be no blood in the person. And you cannot have the blood at too high of a pressure, because you don't want it hurting the patient as it goes back in if you were to apply it to a person. And you also cannot have, so basically you can't have the flow rate going too high. On the last page we have our sources, which is the paper that was wrote on their model that they created, and I believe that is it. Thank you.